So we know that from algebra, the average rate of change of a line has always been called its slope. So then in algebra class, when they would talk about, well, what's the rate of change, you would have been looking for the slope of the graph. Now, also in algebra, though, remember that when we're dealing with lines, the slope is what we would call a constant rate of change, because if it's going up 1 and then over 2, up 1 and over 2, anywhere along the line, that slope is constant. But in real life, actually, very few things are under what we would call a constant rate of change. They fluctuate according to time. And so in real life, our functions tend to look more kind of up and then down, and then even sometimes they, it'll stop for a while. So we usually have, with our functions, a rate of change that changes depending where you are along the timeline. So a lot of times what we do when we're trying to figure out the rates of change, I'm going to move this over, is we start with what we call an average rate of change. And we've talked about how that's simply the slope of the secant line. Now let's graphically, we showed that a little bit with the Usain Bolt video off of Khan Academy, but just graphically so you get an idea what that means, because it's a pretty big concept in calculus to understand the difference between an average rate of change and an instantaneous rate of change. So graphically, in real life, usually this y-axis is time. You can see when I go pull this one up, it's minutes, and same with on the next page, I think it's minutes or seconds. Usually our independent variable is time, and then something's changing over time. And if I were to discuss what happens over a certain interval of time, and I'll just go put, a graph on like this, then I would go to what we'd call A, f of A, y value there would be right here, and B, f of B, sorry. And if I connect them with what we'd call a secant line, that gives us the average rate of change over the interval. It doesn't tell me what's happening instantaneously at any point, but as you squeeze that interval in closer and closer, like if I were to squeeze B in here, 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 and do the secant line, then I am getting really close to what the average rate of change is at the instant. But you can see that for this graph, the rates of change are varying quite a bit. Here, it's quite steep, and then it's leveling out, and here it's going down, and here it's 0. So what tends to happen is we have what we would call varying rates of change. Well, down here on the bottom, I think this is from the 2012 free response part of the actual AP exam, and usually there are 3 parts and they're worth 9 points. Well, part A dealt with this exact concept about using an average rate of change to estimate what's happening at a given point of time. So this situation has the temperature of water in a tub, and it tells you it's modeled by a strictly increasing function. All that means is the temperature is going up continually, not going up the same amount, but it is increasing. You can see that from here to here it went up at about 2, from here to here about 4 degrees, from here to here about 6 degrees. It's varying, the rates of change are different, but it does appear to be an increasing function. And it says that we are having W of T being measured in degrees Fahrenheit. It gives you that the water started at 55 degrees and we are heating it for 30 minutes. And again, the chart doesn't go out to 30 minutes, and that's part of B and C, which I didn't screenshot in here. We don't know, the only thing you guys are equipped to answer right now is this part A. But it says that you are supposed to estimate W prime of 12. Well, first of all, you need to know what that's asking you to estimate. W prime of 12 would be the derivative at 12, which would be the rate of change at 12, which would be in degrees per minute. Whenever it's a slope or a derivative, it's got that per in there. And you'll notice that when I go to the table, I have no idea what's happening at 12. But I do know the neighboring 9 and 15 values, which is why it says to estimate. I can't give you exactly what the rate of change is at 12. But what I'm going to do is use the neighboring values here to find the average rate of change, and we'll use that as our best estimate. And again, the closer you pull that time in, your average does tend to approach the instantaneous. So it says use correct units. All that's telling you to do is to make sure you label your answer. Whenever you label a derivative, you always throw in the word per, because it's a rate of change. Miles per hour, gallons per minute, in this case, degrees per minute. And so what we are going to do is we're going to estimate that using the slope of the secant line. So what we're going to do is we're going to take the fact that we know what's happening at 15, and I could put it as points. I can say that I know that at 9 minutes in, there's 61.8 degrees, and 15 minutes in, it was at 67.9 degrees. Now, I could do it like that. The technical notation would be the degrees at 15 minutes, where it is now, minus the degrees at 9 minutes, over the change in time, which would be 15 minus 9, or 6 minutes. And I could actually, really all I'm doing is finding the slope of the secant line. I'm doing y2 minus y1, or x2 minus x1. But I'm putting in the context of the water heating up. So on the top, what I get is 61 degrees. And on the bottom, I'd have over the course of 6 minutes. And when I divide that out on my calculator, I get 1.01, and it's 6 repeating. And we usually have what's called a 3 decimal place rounding rule for these. By the way, number 1 and number 2 on the AP exam are calculator friendly, so you wouldn't have had to do that by longhand or anything. Now, if this is all you leave, they would dock a point for you. This would have only been 2 of the 9 points, but it's certainly a really easy 2 to get. So make sure when it says using correct units, you just did the degrees on the top per minute, degrees per minute. So what this represents is that I would estimate that at 12 minutes into the heating of the water, the temperature is rising at a rate of about a degree per minute. And I don't know that. I mean, actually, perhaps, I guess that wouldn't have happened because it said it's strictly increasing, but I was going to say maybe they dropped an ice cube in and it cooled off in between there. But I do know that I could use this to estimate. So that would be done. On the next one, I screenshot in another one that's from the 2011, and again, it's in the calculator part. There's other questions they will ask you about this table, and some of them are quite difficult to answer, but this part A with this estimating the rate of change, it's pretty easy. So now on this one, it's this very similar question. I think on last year's they had a cup of tea. So this one's a pot of tea, and the last one was some water in a tub, but it seems to be a trend that they've got some sort of liquid that's either heating or cooling over time. And so this one, I've got a pot of tea cooling. You can see it goes down 6, and then it goes down 8, and then down only 1. But it is a decreasing function. And it says that we are doing degrees Celsius over the course of time. So again, it's not a linear function. That change is not constant, it is varying. But what we're going to use that a table to approximate the rate. This would tell you that we are doing slope. This would tell you that we are kind of thinking of a derivative. That word rate is really important. The rate at which the temperature is changing at 3.5 minutes. And again, you go to the table and you say, well, I don't have 3.5, but I have the neighbors. So we're going to do the slope of the secant line. If I were to graph it, that's what I'm doing. I'm not graphing it, but if I were, I would plot those dots, I'd connect them with a curve, and I'd be finding the slope between these two and using it as my best estimate for what's happening at 3.5 minutes. So when I go here, it says use the data to approximate the rate. So I'm actually looking for h prime of t, and I want to estimate what's going to happen at about 3.5 seconds. And I'd say, well, okay, what happened at 5? And at 5 there are 52. We'd call that our x2, y2, if you were thinking of it more in algebraic sense. And then 2 in, I was at 60. And we would call that our x1, y1, etc. Anyway, so I need to do h of 5 minus h of 2. Really what I'm just saying is y minus y over x minus x. Or if I'm thinking of it in an algebra context, it fell 8 over the course of 3 minutes. So what I get here is a negative 2.667, negative 2 2/3, but we usually do a 3-digit rounding rule on that. If that's all I left, again, I'd lose a point. Although on this one it doesn't say to use correct units, they usually on these word problems want to. So what does that mean? That means that about at 3.5, I'm using my estimate of what happened right next to it, and I'm finding the average rate of change. And so it'd be at about negative 2.667 degrees Celsius per minute. That's the average rate of change that I'm using to approximate the instantaneous rate of change. And those are some good problems. What I would like to do also is just go to a blank sheet of paper to make sure when you go do the worksheet, because your assignment is to do a worksheet. I did link the key on Edmodo. I would highly suggest you go through it on your own and try to do it before you go look at the key. I can't prevent you from just going and copying it, but I would not do that. It'll catch up with you there, especially there's a quiz next week with some similar questions. So make sure you understand what you're doing on that as you look through the key. But one thing I want to reiterate before I quit here is that when you have a function, and I'm just going to make a fake function that's going all over the place here, like this, there's going to be several questions on your worksheet that talk about different things like f of a. Oh, let's go talk about this, and let's make sure when it talks about just what is f of a, alright, it's looking for that y value of the point. So if this hit up here at 5, I would say f of a equals 5. When it just wants the f of, that means the y value at. So make sure that's just looking for the y values. So if it says, you know, calculate f of 4, it's just the y value at 4. It's very straightforward. When it asks you to do some estimating, maybe it might say, where on the graph is f prime of x equals 0? What that's saying is where's the derivative equal to 0? Where's the slope of the tangent line equal to 0? And on this graph, that happens right here, basically every time it changes direction. Here, and right here. So it was going down and then up and down. We have a derivative of 0 at all of those points. If it were asking you to estimate the derivative, maybe this is the point, I don't know, 4, and it says estimate f prime of 4. And you would say, okay, well that's going downhill pretty steeply. I'd say it's about negative 3. So keep in mind whether it asks you for f of, which is just the y value there, or f prime of, which is the slope of the tangent line there. There may also be some questions of, sorry, I'm always doing this during my prep and it's during lunch, so the bells go off like crazy. Remember when it's asking you to find the average rate of change over an interval from A to B, we call that the slope of our secant line. And again, that's not exactly what's happening, because you can see right here, it's actually, slope is positive, here it's negative, here it's 0, but if I do the secant line, I'll get the average that happens over that interval, and when you kind of squeeze that in, it does actually become closer to the instantaneous at the point. But again, if it asks you for an average rate of change over an interval, that's just the slope of that secant line through A, f of A, and through B, f of B. So you simply would say that the average rate of change, and sometimes it'll say over the interval AB, or it'll say on AB. General rule of thumb is that it's just y minus y over x minus x. This gives you the average rate of change or the slope of the secant line. And last up, the instantaneous rate of change is what we call the derivative. And that requires some more work, but graphically you can estimate it. Again, if this was 6, you'd say f prime of 6 looks